Right. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to continue our lecture on discussion, a lecture on surface integral. So before we start, together we recite doa. Bismillahirrahmanirrahim. Allahumma aftah alayna hikmataka wa anshur alayna min khazaini rahmatika ya arhamar rahimin. Rabbi shrah lana sudurana wa yassir lana umurana wa hlul 'uqdatam min alsinatina yafqahu aqwalana. Rabbi zidna ilman nafi'an subhana fahman nafi'an. Amin. Bismillah tawakkalna 'ala Allah la hawla wa la quwwata illa billah. Aliyyul azim. Right. So previously we learned about line integral. So the most difficult part, the main content is about parameterization on the path of the line. So today we're going to do a surface integration. Almost the same case. I think we use the same case of the river flowing and there is a leaf or water flow. So like a previous one, so we have an analogy for function of parameterization, which is it's all about the vector field. Sorry, it's all about the vector field. Yeah, the vector field of the river flow or water flow. So it's being uh, cut- uh, being captured the water flow, or we analog the water flow with the vector of w as we used previously, which is a w in the direction. So for this case, because we are talking about the surface, right? So um we need to place we need to imagine that we place a net vertically to the river. So this is a river one. So this is a net. So the net direction should be vertical, perpendicular to the direction of the water flow, right? So almost every part is in 90 degrees or um, the perpendicular, the direction of water flow is perpendicular to the surface of the net. So suppose we want to calculate the amount of water through the net at some particular moment in a time. So basically, when we want to calculate amount, we will talk about the container. We say water flow, and then we want to measure how much, how many. So normally people, or the easiest part is we have a container here. So the container will collect all the water throughout that pass through the net. So that is the most straightforward calculation or straightforward observation and data collection. But in mathematics, we can also determine the rate of water flow or the amount of water flow by using a surface and surface integration, and also the the vector field that represent the water flowing. So let's say, so this is the surface. Let's say this is a surface. Okay, so denote that the vector w represent the flow of water. So you have surface, and then the water flow. The vector representing the flow of water, and n will be the vector which is perpendicular to the net. So first the net. So this is your perpendicular. This is an n, normal vector respect to the surface. W, somehow for this under this example is to make it easy, it is on the surface, same direction of the surface, surface of the net. So if the net is parallel to the direction, if the net is parallel to the direction of the water flow, then no water pass through it. So definitely, if you have how can I visualize it? mm, you have net, right? So this is your net. So look at this, the net at from the side view. So basically, if you imagine this is a net is only a few millimeter thick, ketebalan dia. So imagine this is your net, ketebalan net tersebut. Your eyes from here, you look at it as a fabric, something like that. So if the water flow is um, um, parallel in the direction of this one, so this is W, so we can say that there is no water pass through it, so it is not 90 degrees lah, and is perpendicular to W. The most water pass through the net when the net is perpendicular to the flow. The maximum of water flow is when W perpendicular with the surface or net surface, right? Definitely lah. It stands to reason then the amount of water flowing through the net is proportional to W dot N. So the total amount of the water flowing is in maximum is W dot N, which is the W should be within the same direction of N. So we have a dot product, so W dot N, it is a dot product, we give you scalar value, which is a maximum amount. Alright. So now let S to be the surface. So now at the first place, W is the same plane with S. So W now, which is same goes as, it's not in direction but in the plane, surface, right? So the surface is parameterized by psi. So the surface itself have what we call it, have parameterized function of psi. So psi is a parametric of U and V, which is lies, maksudnya dia duduk di atas, dia duduk di permukaan net, lies on the net. So this one is lies on the net, as same goes as S, which is the surface. So now the vectors of d psi over du and du over dv are both tangent to S. So if when you have a surface like this, make it slightly inclined. So this is surface, imagine this is surface, and this is a S surface of the something. So d psi over dw, now d psi, because psi is a parameterized that lies on the surface, on the surface, so on the surface. So d psi over dv and d psi over du is actually it's a tangent. Tangent means that it also lies on Allah. It also lies on here, on this one. This is d psi. Maybe it can be like this or like that, d psi over dv and d psi over du, which is tangent. It's not perpendicular, but it's tangent, which is, it is on, lies on the same. So then when you have d psi over du cross d psi over dv, so as we discussed, or as I said previously, if you cross product within two vector, you have a perpendicular. So definitely d psi over du, so using your right hand, so you have n here, the normal vector of cross product between d psi du and d psi dv. This one should be du, sorry for the mistake on the writing. perpendicular or normal to S, right? Definitely. So this is what I said. So this is S, your surface. So this side, the N is perpendicular to S. So now let W be a vector field representing the water flow, and W psi UV is the vector of W at any point. So now W also is on the surface as well. So the total amount of water through the S is given by the integral, this one. So you have to double integral of the vector W, which is a water flow, which is also in the same direction with the surface of the net, with parameterization of the UV. This is parameterization. Dot cross product, which is a normal vector du dv. So we call it the surface integral. W over S is denoted by W over W dot ds. W, which is a vector on surface, which is parameterized by psi, and also ds is the surface, the total surface of covered area, which is what we call it, that one, the net surface. So this is the equation, this is the formula, meaning that you need to have double integral, and then you have dot within your n, the normal vector, which is the normal vector that have been parameterized by this side du, this one dv as well. So du dv, right? So this is the formula, and the integral is over S, over the whole surface. So you have surface and ds, which is water flow being integrated on the surface of the net. Okay, that is a theory. This one is a theory. I think it quite complicated to understand, but since we are going to do some calculations, so from this one, I hope, from the example, I hope you can understand more. Otherwise, you just focus on the step how to solve it, and maybe there also a step by step to check and do the integration. So from that, maybe you can have a better understanding. Let's say the W itself, the water flow, is being given by a vector W, X, and Z, which is all of these component being parameterized by psi, which is in the parameterization terms of theta and Z. So when it involves theta and Z, so definitely it is something that rotating, or something that can be related with cylinder. So if you understand if you have a look at the cylinder itself, you have a parametric or coordinate on theta and phi. So you have theta, so you have phi, z, you have z also, z, and you have phi as well. Okay, so for this one, it was only used theta and z. So meaning that we only considered the theta and z. Definitely for this one, we didn't care about the phi. All right. So it's given that the parameterization is cos theta, sin theta, and z. Within the theta lies within 0 until pi over 4, which is 180 divided by 4. And also, but since we use the radian mode, we need to use the radian mode within cylinder parameterization. So z is from 0 to 1. The vector -1, 0, 0 is defined an orientation of S at the point 1, 0, 0. So what is the orientation of S? It's given by a vector. Given, it said the vector of -1, 0, 0, which is in the x direction, negative x direction, it is an orientation at point 1 0 0. So as x equals to 1, so meaning that you have here, for example, for instance, you have here point, and then the vector is downward, negative 1, right? So this is 1 0 0. So hopefully the figure or the diagram can make us much easier, help us to understand much easier. So we now compute the integral of w. So what is w? So the as w is again is a vector on the surface as well, with this orientation. So first with s over the s with this orientation. So first we need to compute the d psi over d theta. Like previous one, we have d psi over d v and d psi over du. Alright, so another one is d psi over dz. So what is your psi? Cos theta, sin theta, and z. So first we differentiate, partially differentiate in terms of theta. So you have cos becomes negative sines, and your sine become cos, z becomes 0. So there's no point of that. And also d psi over dz, again the same parameterization respect to z. So you have 0 0 1 for sure, because this one is 1, and then okay, that's all. So next is do the cross product. So because it is according to the equation given here, so you need to have a cross before you have a du dv. So cross product. So from cross product, you know that using the cross product, negative sign. So this is the part of sine, and also the part of dz. Partially psi over z component. So using this one, to get the first part is cos minus 1 minus 0, cos this one times and minus d0. So you get cos theta minus 0 for the x component, and as for the j component, you have need to this one, sine, negative sine, minus ad, negative sine, minus 0. So this part you get positive sign here, and then the last part is plus, right? Plus the component on here, I just give this negative sign 0 0. Okay, so this one should be 0. So from that cross product, you get this vector, so is equal. Okay, now so notice that at point, okay, so now we need to testing. Same goes as the previous one. So if when we do line integral, so we also check on the orientation part. So for curl or for surface integral, we are supposed to do check on the vector direction. So now notice that at point 1 0 0, at point 1 0 0 as given also at s point 1 0 0 for this one, at point 0 0 the parameterization give you definitely 0. Okay, all right, so parametric is 0, but the vector of normal vector d psi is equal to 1. So what is this one? Is this equation. So then we substitute of 1, 0, theta 0, and z 0. So you get definitely cos 0. Cos 0 equals to 1, and sin 0 equals to 0. And 0 is nothing to use lah. So this means that the normal vector is on positive x, which is the normal vector is on opposite side. So this is your n, or d psi, d theta cross d psi, partially psi, partially z. So this is a normal vector, which is it's not in the direction of on the surface. It's not in the same direction as given by the vector. Vector C should be downward on the x component, but somehow our cross product give positive orientation. This is exactly, see, exactly opposite specific orientation of S. So should be S in the negative at point, negative value, which is the point of S should be in the negative of X component. So but somehow our normal vector, as we said previously, the S is in the direction cross product. The S is on the surface, so the cross should be like this one. And then for the surface integral, so we need to have a surface integral. The vector of S is not in the same direction of N. It is not 90 degrees as well, but it is 180 degree difference. So meaning that if we use parameterization of psi to compute the integral W over S, we need to remember to change the direction of our final answer. So this is the key. Same goes as the previous one. For the line vector, we need to check the gradient, and then we need to check if the gradient doesn't give the same answer as the vector. Have a look at that lecture note as well. So that one will will become the indicator for us. So then we can we need to change the direction. Okay, so this is the thing here. Okay, 2 times. First, integral from d theta. Alright, so with d theta first, from 0 to pi over 4. So theta sit here, from 0 to pi over 4. And then the second integral of z from 0 to 1. So this is the thing that we are going to integrate step by step. It's not difficult, but it's quite straightforward. First, sine times cos. We got the sine squared, sine cos theta, sine theta, cos theta, cos theta, sine theta. So again, this is plus. So you have sine theta, cos theta, plus sine cos theta, theta, and then that's it, dz. So this part is actually from the identity becomes 2 sine theta cos theta. So this is the identity, right? So it just twice. Sorry, this is not identity. Identity is squared one. So this is not identity. It's just adding 2 same vector. So you have can be right as this one can be change the position, because this is multiplication, right? Only multiplication, so you can have change position. This change position. So you have twice, so you have 2 sine theta cos theta dz. So this is okay. First, we need to integrate over d theta first. So what we have, sine theta cos theta, integrate. So using the identity, this one can be written as sine 2 theta. So this one is identity. This can be written as sine 2 theta. So meaning that we have much easier. I mean, the work that we are going to integrate is quite easier, because it involves only component of this part. So we can see that first for this theta, so we need to integrate first with sine, and it becomes 2 theta, and then we differentiate this one. 2 theta becomes 1 over 2 theta to 1 over 2. Wait. I think this one also adapt from the identity, because this involves 2 theta. Yeah, it is also from the identity of integration 2 theta. It's not a simple integration, this one, because it's involved 2 times x inside the component. So as what I remember, yeah, definitely when we integrate, it becomes cos, and then we need to divide it by its integration, 2 theta, it becomes 2 on the downside. So it's become negative cos theta, and then divided by, we differentiate here, 2 over theta, okay, so from 0 to pi, so definitely this one is straightforward. And then for dz, so after you substitute, you get 1 over 2, so 1 over 2 dz equals to 1 over 2z from 0 to 1, so it's become 1 over 2, definitely, because this is z, this you just substitute 1, right? So as parameterization, okay, since this is checking part, if the vector is the same, so you just straightforward take the answer. But the vector orientation from S and d psi over d theta, from surface and parameterization, is in opposite side, opposite sign. So when this thing happen, so we can just straightforward change the sign. So the sign of the parameterization of integration on the surface, so under this component, is equals to half, 0.5. all right, so this is the example part. I know it's not too complicated, but it quite quite a lot of thing. I mean, you need to do step by step. Okay, so for the problem, so I already put the solution here. So the only part for this one is not it's not given the step to solve this problem. So I just let you try it, or we want to discuss during our tutorial discussion also can. So I think you can have a look for problem 1 solution first. Almost the same thing is being given, parameterization, so take derivative and then do cross between 2 parameterization vector, then you get this one. So this is involve identity maybe. So then that's we need to check. So after we check the at point, so at point 0, at point 0 2 pi over 2, 0 pi over 2, which give us 1 0 0. The vector is in the same direction. Okay, so we given given by vector at point 1 0. So you need to check first at given point 1 0 0. So you need to substitute of 1 0 0 on the parameterization. So for 1 0 0, so you have 1 and 6 0. So when you have 1 0, put it here, you have 1 sine cos 0 equals to 1 theta phi equals 0 sine 0 0 for pi over 2, from 0 to pi over 2 1. You need to have okay, and then check the vector field. Okay, do the same step. Okay, it's quite long, so I think for this part we will discuss in our tutorial, inshallah, this week. For on the week 9, inshallah. So that's all for this lecture. I think hopefully you can get what I have discussed here. So If you have a question, later on we will discuss in our tutorial or our lecture session. Thank you and assalamu